Good evening, it's Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. Today we will continue the structural equation modeling. So in the last class we have briefly highlighted the issues, or you can say various concepts behind structural equation modeling. So today we will specifically highlight the methodological issue and its applications. So structural equation modeling is a generalization approach to multivariate data analysis. So we are jumping from single equation to simultaneous equation and simultaneous equation to structural equations. Okay, structural equation in modeling, structure is very important. Okay, so we have to see how is the setup of structural equation modeling. So now, so here the most important agenda is to find out the proper structure, to find out the proper structure. Okay, find out the structure is the main agenda of structural equation modeling. So I have already mentioned structural equation modeling. It is approach to analysis of covariance. It is the structure of analysis of covariance. Okay, then analysis of causality. This is analysis of covariance, analysis of causality, covariance, or you can show that we can mention that it is covariance, analysis of correlation. Okay, analysis of causality one way, and third analysis of causality 2H. Okay, this is one way causality, this is two-way causality. Okay, so you see this particular two things will be called as a, it's purely on regression analysis. Okay, it is nothing but the root of regression analysis. In fact, correlation and regression is the same groups. So here we means obviously if you will say regression, then we are discussing the R square, and which is the correlation coefficient for a bivariate setup. So in fact, multivariate setups, it may be multiple correlation coefficient. So regression analysis basically deals with the causality issue and correlation issue. Then there is the analysis of causality in the two-way interdependence techniques. So that is what we will call as a FA, factor analysis. Okay, it's called as a factor analysis. So structural equation modeling is the integration of factor analysis plus regression analysis. Okay, factor analysis plus regression analysis. So now if you will integrate these two, then obviously we have to highlight certain things here. So that means first thing is to test the relationship among the variable, to test the relationship, or to examine the relationship among the variables. Okay, variables, to test the relationship among variables. This is first objective. And specify the models that explains the data, specify the models that can incorporate the existing data. Then you need to have a flexibility, with respect to continuous variables and discrete variables, because structure cannot be directly connected with either continuous variable or discrete variable. So you need to have a integration about continuous variable and discrete variables. For instance, that is how sometimes we use dummy variables. Some of the variables we cannot you can say quantify properly, so we have to go for a qualitative way, and we have to categorize in such a way by using PROSI. So as a result, the modeling structure can be properly evaluated. So okay, so this is another interesting agenda of flexibility. Then significance of testing, significance significance of testing, and you can say model fit. Okay, significance of testing and model fit. These are the specific requirements so we need to have in the case of structural equation modeling. So structure is very important, and within the structure we like to know, or we like to establish the relationship among the various variables and specify the exact models, so that we usually call as a path models. Then to have that one, so you need to have a little bit flexibility or compromise between continuous variable and discrete variables. Then then obviously we have to highlight the significance of this testing and model fitness. Okay, with this basic framework, so we have to highlight the detailed structure about the structural equation modeling. Before I highlight, I let you know little bit historical background behind the structural equation modeling. The structural equation modeling root is from psychology. Okay, structural equation modeling origin. So once you know the origin, then you can get to know on these features, why these features are already means you need to have in the case of structural equation modeling. For instance, flexibility. So suppose the flexibility between continuous and discrete is there. So most of the variables in the psychology is very discrete in nature. Okay, so once you have a sometimes structure, so we need to have a integration otherwise, or flexibility, otherwise it is very difficult to handle. So okay so the first origin is the psychology. Okay, psychology. Okay, it is called as a, because the origin before we going to structural equation modeling, I will give you the historical background how this structural equation modeling coming into the picture. So in the psychology, the most interdependence technique is called as a factor analysis. Okay, then we have a human genetics. So human genetics will give you the approach of regression and analysis, where the Galton has started the studying the height of son and fathers. So they propose the idea of the regression analysis. Then biology, it is the detection of path analysis. Okay, then fourth, economics, it will give you the structural equation modeling, simultaneous equation modeling. Okay, then we have the integration of statistics. In the statistics, it is the methods of maximum likelihood estimation. It is the method of maximum likelihood estimations. Okay, maximum likelihood estimation. So that means you see here, so to know the structural equation modeling, so you must have knowledge on factor analysis, regression analysis, path analysis, simultaneous equation modeling, and maximum likelihood estimation. So the integration of all these together is called as a structural equation modeling. So that means you understand yourself how complexity is this particular problem. So structural equation modeling is the highest setup of this econometric modeling. So here, so there is use of various individual techniques like factor analysis, regression analysis, path analysis, simultaneous equation systems, then maximum likelihood estimations. So that means it is the core area where psychologists, human genetics, biology, economists, and statistician can work together, or you can say integrated together to have a particular solutions. Okay, so this is the basic framework of this simultaneous equation modeling. Okay, so now, so what is exactly the you can say this particular structural equation modeling. So structural equation modeling, as I have already mentioned, there are two sets of structures. One is called as a structural equations, and another setup is called as a modeling. Okay, so that means here we have to find out the proper structure in an equation form. Okay, and modeling, here you have to transfer the generalization problem, theoretical problem, into mathematical form. So in this mathematical equation you must have some structures, so that is how it is called as a. So that means you bring the structure and you bring the modeling, then if you integrate you will get the structural equation modeling. Okay, so now the issue of structural equation modeling is consist of two things. So it is called as a latent variable and manifest variables. So now so far as the structure is concerned, it is the root for two things. Here is called as a latent variables and manifest variables. Okay, latent variable and manifest variables. So now the structure is that, so you have to find out the proper structure here in between the latent variable and manifest variables. Manifest variables means observed variables which are in the form of both exogenous and endogenous. They are very much observed. It is readily available, means that's why it's called as a data files. Then within the data files we have to find out a structures, so that is in the form of a latent variables. Okay, latent variables. So now we have to find out how latent variable has a close connection to each other again. So that means it is all together three pillars. Okay, three pillars of the system. So one pillar is the endogenous setup, then latent and endogenous, then another pillar is the exogenous setups and exogenous latent. Okay, so it is integration between endogenous setup and you can say exogenous setups, endogenous latent and exogenous latent. Okay, within the basic step setup, then we have to highlight this particular setup. Okay, so now so far as the structural equation modeling is concerned, so as I have already mentioned, basically we look for regression analysis, then second thing is correlation analysis, then obviously third thing we like to highlight the model fitness. Okay, overall model fitness. Okay, overall model fitness. Generally you see here it's a very interesting thing because it is integration of so many things together. So starting with regression analysis, factor analysis, then path analysis, and then simultaneous equation systems, then maximum likelihood estimation, etc. But basically our observation is very limited here. Means we like to know where is the means once you will apply the particular structures, where we will set the regression and where we will set the correlations. Okay, so obviously it is the game between the regression and correlations. Okay, so but factor analysis and path analysis will give you the entire setup of structure only. So the general framework which we can highlight here is like this. So when we will go for correlation, then it will give you degree of associations. Okay, degree of association. Okay, so this when we will go for regression analysis, it will give you direction of causality. It will give you direction of causality. So it is obviously one way causality. Okay, it's not like this. Okay, it should not be like this, because this is not allowed here in the case of structural equation modeling, which is very much allowed in the case of time series modeling, pure time series modeling. So here core objective is to find out the degree of association, that is your degree of degree of relationship between two variables, means within the particular of course it is a multivariate framework. So every time we like to know how these two variables are related to each other. So that means it is the degree of association within that particular systems. We have to, there may be many variables, say 10 variables. So we like to know 5 endo and 5 exo. So we like to know one variable endo with another variable endo, how they are related, whether the structure is the causality structure or it is the associations relation, only simple relations without having causality issue. Okay, so that is how we have to bring this issue. So now in the simple setup, you see in the simple setup, so we like to know what is the degree of association among the variables, then causality issue, then model fitness test. Okay, just like when we will go for regression analysis has a two specific objectives. One specific objective is what is the direction of causality, and another specific objective is what is the goodness of fit, that is what is the goodness of fit, which we will measure in the form of R squares. Okay, so that means the value of R square is the value of R square lies between 0 to 1. So close to 1 or equal to 1 will give you higher accuracy, higher model fitness than the R square close to 0. If it is close to 0, it is unfit, or it is you can say not suitable for this modeling. Okay, so this is how we have to represent this. So altogether, so we have to find out the regression coefficient, correlation coefficient, the significance of regression coefficient, significance of correlation coefficient, then finally overall fitness of the model. So when we will go for regression analysis, so here we have to find out the regression coefficient. Then when we will go for correlation, you have to find out the association coefficients. Okay, so then finally if we club together, then we have to find out the model fitness test. So like in the case of regressions, model fitness test is usually, you can say not usually, every time it is with respect to R square only, coefficient of determination. Here model fitness can be observed with many indicators. Okay, so I just briefly highlight three main indicators through which we can represent the model model accuracy. That means once you prepare the structure, ultimately the complete model is with you. So whether that model is systematically okay or not systematically okay, it's very difficult to say without having sufficient indicators in your mind. So here the sufficient indicator is there is some kind of reliable indicators through which we have to justify the model reliability. Okay, means fitness of the model. So that is why I have mentioned here model fitness. So how do you observe this model fitness? There are many indicators are there, but briefly I will highlight three indicators. One is called as a goodness of fit index, then adjusted goodness of fit index, then third one is called as a standardized root mean square residuals, Okay, goodness of fit index, it is nothing but the formula is 1 minus chi-squares for the default models, divided by chi-square for the null models. Okay, null models. So this is the GFI goodness of fit index. So now for if GFI is greater than to 0.9, then model will be considered will be accepted, or it is considered as the reliable models. Okay, so if GFI, that means GFI is higher the GFI, greater the possibility of accuracy of the model. If lower the GFI, then obviously model accuracy or model reliability is very low. This is one of the indicators through which we have to justify the model fitness of the structural equation modeling. Okay, then second is the adjusted goodness fit index, which is nothing but 1 minus GFI, okay, goodness fit index, okay, multiplied by degrees of freedom of your model divided by degrees of freedom for the baseline model, Okay, baseline models. That means in the case of regression analysis, we use R square and adjusted R square. Adjusted R square is nothing but 1 minus R square into n minus 1 by n minus k. That is means adjusted R square means we have to adjust with the degrees of freedom. Here also we are just doing the same thing. Generally the component is goodness of fit index. So now it has to be adjusted through proper degrees of freedom, because ultimately it is many variables game. So once you involve more and more variables in the system, then obviously it will affect the degrees of freedom. Okay, so that degrees of freedom has to be taken care. So as a result, AGFI will be another indicator has to be used, which can take care the overall fitness of the model, and in the same times it can take care the, you can say, degrees of freedom. Okay, if AGPI is greater than to 1 or equal to 1 means it is a perfectly fit of the models. Means model perfectly fit if it is greater than to 1. Then if it is less than to 0, then model is poorly fit. Okay, so that's why you have to be careful how you have to find out. Then it's a standardized root mean square residuals, which is the average difference between the predicted and observed variance covariance in the models. Based on this, based on this standardized residuals. So when this SR is equal to 0, then obviously it is perfectly fit. When it is greater than to 0, then obviously it is totally unfit. Okay, so that's why it should be close to 0, it should be close to 1. Okay, and it should be also greater than to 1. So in this scenario we have to observe the model fitness of this particular, you can say, structural equation modeling. With this basic frameworks, so we like to highlight the structural equation modeling. Okay, the structural equation modeling, you see here, it is I will give you two different models. Okay, with a simple structures, and then we will go for a complicated structure. So you see, so I have mentioned structural equation modeling. Structural equation modeling is the game between factor analysis plus, you can say, path analysis. It is a game between path models and factor models. Okay, factor models, factor analysis or path analysis, or you can say factor model and path model. Let me highlight what is factor models. Okay, factor model means we start with like this few variables, say x1, okay, x1, then x2, okay, like say I'll take for simplicity, I'll put 3 variables only, then x3, okay, then okay, x3 since I mentioned here, so we'll let's say go for xk. All right, xk. Then similarly you see here corresponding to this one, so we have to create epsilon 1, epsilon 2, epsilon 3, epsilon k. Okay, then these are all latent symbols, these are all latent symbols, these are all observed symbols. Okay, these are all latent symbols, these are all observed symbols. Then followed by delta 1, delta 2, delta 3, delta k. Okay, so now how it is related, you see, epsilon 1 depends upon x1, x2, x3, xk. Similarly epsilon 2 depends upon x1, x2, x3, xk. Epsilon 3 depends upon x1, x2, x3, xk. Similarly epsilon k depends upon x1, x2, x3 and xk. So this is how the structure of factor modeling. Okay, so means it is all together very interdependent. Okay, so that means what is the basic agenda of factor analysis is that, so you have a set of observed variables. Okay, so we have to create a latent variable. Latent variables means you have to find out a new form of the variables. You have to create a set of variables which is a linear combination of original variables. So of course we have to assign with some weightage. Okay, so I will mention here how the weightage can be considered here. So let's say here, so x1 is equal to here lambda 1 1 epsilon 1 plus lambda 1 2 epsilon 2 plus, you can say, continue. Okay, so lambda 1 k epsilon k plus delta 1. Okay, similarly x2 equal to lambda 2 1 epsilon 1 lambda 2 2 epsilon 2 continue lambda k lambda, this is 1k. Okay, so this is 2k epsilon k plus delta 2. Similarly you continue. Okay, so then xk is equal to lambda lambda k1 epsilon 1 lambda k2 epsilon 2 continue plus, of course, here lambda kk epsilon k plus delta k. So this is how this system will operate. So that means it is nothing but the picture will be like this: xi equal to lambda ij f plus delta I. Okay, so this is how it's called as a factors. Okay, so that means this factor has a means this is the variable which is integrated with some factors and its weightage with error terms. Obviously as per any type of statistical analysis, error will be obviously must. So whether you will go for regression analysis, or whether you will go for factor analysis, or whether you will go for structural equation modeling, so error will be always must. So with the particular setup, so we have to bring how quickly you have to set up the structure to analyze the particular relationship. Okay, so this is how you have to observe. So that means how do we construct all these things, means so far as a factor is concerned. So there are many methods you can use to transfer original variable to new form of the variables. You can apply maximum likelihood estimation methods, centroid methods, or you can say you can apply principal component analysis. Generally, principal component, which is popularly known as a PCA, is the most important technique which can transfer the original set of variables to smaller number of variables, which is the linear combination of original variables. So now how do you proceed mathematically? It's better when you have observed variables, then you find out the variance covariance matrix. So with the basis of variance covariance matrix, then we means variance covariance matrix with respect to its correlations. That means it's a correlation. Variance covariance means, like suppose there are three variables, x1, x2, x3. Then this side x1, x2, x3. Then obviously we have correlation R11, R12, R13, R21, R22, R23, R31, R32, R33. Okay, so this is how the matrix can be designed. Okay, so now with the moment you have a number of variables, forget about endogenous variable or exogenous variable. For factor analysis, it is not required at all. So factor analysis, we are assuming that all variables are interdependent to each other. So there is no way to classify which one is the dependent structure and independent structure. But when we will go for regression analysis, there is such classification. So now you see here, so the structural equation modeling is the integration of two techniques, where one is the need of the classification with respect to dependent and independent, and another technique which does not require the classification dependent and independent. So now we have to find out, we have to the aim of the factor analysis is to transfer the original variables into some latent variables. Okay, then regression analysis will observe how the latent variable has a relationship with the other variables. Okay, various latent variables and other variables. Okay, so this is how the structure is all together we have to discuss in the case of structural equation modeling. So now you get to know what is the factor analysis and how you have to construct the factors. So factor analysis, which is the weightage of various observed variables and the error terms. Okay, so here our agenda is to minimize the error term. That is, the latent variable, variance of latent variable depends upon two variance. One is the common variance and another is equal to error variance. So every time you have to minimize the error variance, so that the construct of a particular factor will be more practical, more feasible, and it can be useful for you can say model forecasting, or you can say policy use. So with this particular setup, so we like to highlight means I will highlight here two different structural equation modeling. So one is a simple one, another is a little bit complex ones. Okay, so we start with the simple models. So you see here, let's say this is structural equation modeling, case 1, structural modeling case 1. So here, so I will take few variables, say like this is x1, this is x2, this is x3, and this is x4. Okay, like let's say xk. Okay, then I will call it here, just I am integrating this what we have discussed in the case of factor analysis right now. So with the help of this factor analysis, so I briefly highlight little bit something more, and we like to integrate with respect to structural equation modeling. Okay, so now I will put it here. Let's say epsilon 1, epsilon 2, then epsilon 3. Okay, then you can say okay, you put it epsilon 3, only 3. Okay, there are 3 items only. Okay, so then that means it's not like that way. If there are n number of variables, you will create n number of factors. It's not like that way. So there is a proper technique how many factors you have to construct actually. So with the basis of technicality, so we have to we have to find out how many factors we can able to construct in this particular available information or available data. Okay, so now if this is the case, then obviously you have to make an integration. You see here, so x1 has a connection is like this, x1 x2 x1 has a connection like this, x1 x3 has a connection like this. Similarly, so we have x1 like this, then we have x3 like this, then you have x2 like this, x3 like this. Okay, so it's better you connect like this. Okay, this is okay, then similarly in this is okay connected, this is connected, then this is has to be connected, this has to be connected. Similarly this is already connected, this is already connected, so you have to connect like this way. So this is how the factor analysis. So now what you have to do, so you like to know this is the relationship you have to see here. Okay, so how quickly they are related to each other. Okay, so many relations you can find out in between all these two. Okay, so this is how the picture all about this this is simple structure of, you can say, structural equation modeling. So how the system are correlated to each other. Okay, so here here what you have to do, this particular line will give you the indication of regression coefficient. Okay, so this particular line will give you regression coefficient. Okay, so that means you see when we will go for factor analysis, then obviously every factor has a summation of let's say lambda I xi. Okay, so the lambda is the coefficient to particular independent variable like this. Okay, fi equal to summation lambda I xi. Okay, I equal to 1 plus, you can say, delta. Okay, plus delta. Okay, the way you have to minimize, then obviously delta will be removed, then finally you will get lambda 1 x1, lambda 2 x2 up to lambda k xk. Okay, so lambda 1, lambda 2, lambda k, these are all weightage. Okay, in the regression analysis, these are the coefficients which you have to observe. Okay, so now this is how the lines are, these straight lines are means it is an indication that we have to means it will recognize the regression coefficient. That means it is the causality issue from this to this, how they are integrated, and what is the weightage factors. Okay, so is it high or is it low? So this is how we have to observe. So that means this lambda I, all these things will be coming here only. So this is in the straight line only. So this is the regression weightage. Okay, or otherwise called as the regression coefficient. However, this row, this row, the indication, this one is a correlation coefficient. This is the indication of correlation coefficient. This is the indication of correlation coefficient. Correlation coefficient. Okay, this is how we have to observe like this to you can say prepare a structural equation modeling. Okay, so I will go a little bit advanced than this particular structure. Okay, this is okay. So now once I will go a little bit advanced, then obviously I will put like this. Okay, let's say this is x1, x2, x3, then x4, then continue up to xk. Then obviously we have the same latent variables, lambda epsilon 1, epsilon 2, then epsilon 3. But you remember these ones. This particular symbol is the observed symbols. Okay, observed, this means it's readily available, and this particular symbol means it's a creative, it's a latent variables. Okay, latent variables, we have to artificially create these ones, latent variables, which is not directly available or observable. So this is the connected. So now we have to connect like this way. Epsilon 1 depends upon x1, x2, x3, x4, xk. Similarly, epsilon 2 depends upon x1, x2, x3, x4, xk. Similarly, E3 depends upon x1, x2, x3, x4, and xk. Alright, so corresponding x1, so then obviously we will call it delta 1, this is called it delta 2, this is called it delta 3, this is called it delta 4. Okay, this is called as a delta k. Okay, this will be supported by delta k. Alright, so now obviously this is also some you can say let's say zeta. Okay, so zeta 1, then this is zeta 2. Okay, this is zeta 3. Okay, so this is how the indications this is how the indication all about. Okay, so this is how the indication all about. Okay, so that means you see here. So now I have already mentioned, so when we will go for structural equation modeling, then obviously there are 4 different shapes. One shape is independent with the independent latent, independent observe or independent manifest with the independent latent. Then another setup is dependent dependent manifest or dependent observe, then a dependent latent. Okay, so there are four pillars to altogether. So independent observes, independent latent, dependent observes, and dependent latent. Then we have to see how this finally independent latent and dependent latent are integrated. So the integration of independent latent and dependent latent is called as a path analysis. However, the moment you will integrate the observe independent observes with independent latent is called as a factor models. Similarly, dependent observes and dependent latent, when you will club, it is called as another factor models. So now we have factor model from the endogenous sites, and we have a factor model from exogenous site. So now together when we will endogenous latent and exogenous latent if we will integrate, then that will create you path model. So that means structural equation modeling is the integration of factor modeling and path modeling. So we have to find out particular structures. So that structure will give you means will be analyzed with the help of factor analysis and path analysis. So this is one part of the problem where we have observed the independent clusters with independent latent. So that means it is lambda 1 is you have to calculate like that way. X1 equal to means when we will calculate latent variable 1, then obviously so here the error term is involved and here the error term is involved. That means you see these are all variables, so these are variables are not fully involved. So it is error component is delta 1, this is error component is delta 2, this is error component delta 3, this is error component is delta 4, this is error component delta k. Similarly, in the case of latent variable 1, epsilon 2 and epsilon 3, so the error which we insert is zeta 1, zeta 2 or zeta 3. Okay, so now this is one part of the problem, so where we are integrating a exogenous cluster with the exogenous latent. So similarly, we have to create another factor models where endogenous cluster will integrate with the endogenous latent. Okay, let me highlight here. So this is another way. So I will put some variables y1, so y2, okay, y2, then y3, so it will continue say yk. Okay, so these are all you can say and endogenous variables. This is endogenous variables y, so this symbol will be indicates endogenous variables. Okay, that means it's observed variables. Then we have to create a latent so let's say this is eta 1, then this is eta 2. Okay, eta 1 and eta 2. So now how is the connection? Eta 1 has a connection with y1, y2, y3, then yk. Similarly, eta 2 has a connection with the y1, y2, y3 and yk. Okay, so this is how then obviously its error component is you can say epsilon 1, epsilon 2, epsilon 3, okay, epsilon you can say k. Okay, so then this is the error component which you put it is a zeta 1, okay, and zeta 2, okay, zeta 2. So this is error component, okay. So that means this is called as a eta 1 and eta 2 is called as a latent dependent variables, okay, and y1 y2 is called as a observed dependent variables. It's called as a observed dependent variables or manifest dependent variables, okay. These are all error terms. These error terms are for dependent clusters and these error terms for latent dependent variables, okay. So this is another side of the problem. So this is one part of the structural equation modeling, and which we have just discussed another part of the regression modeling, means structural equation modeling. So now we have to integrate the both latent independent to latent dependent. Then we will find out, is there any structure between the latent independent to latent dependent. If that is the so, then it is called as a path model, and we like to integrate this factor model with the path model. Then we will highlight the issue of, means it is the question of the structural equation modeling. So that means there is a need of some path. So that path is nothing but a structure. So if there is any structure, then obviously path model and factor model will give you the structural equation modeling. If there is no such path, then obviously there is no question of structural equation modeling. So you have to just end with this factor analysis only. Transfer the variable, find out the weightage, then you have to analyze with the different issues, okay. So now here we have to see whether factor analysis can be applied to this particular problems. That means we have to transfer the original variable into some latent variables. Then similarly, means in the independent side, similarly in the case of dependent side, you have to transfer the original setup into the dependent latent variables. So now I will club these together, then we will see what is the results here. So now the moment I will club these two together, then it will come like this way, okay. So what I will do here, so you check it here, this is x1, this is x2, this is x3, continue, this is xk, okay, this is xk. So similarly, so what I have done, I have put epsilon 1, epsilon 2 and epsilon 3. So this is latent, so the symbol will be like this, alright. Then other sides, so we have y1, y2, y3, then yk, okay. It's not necessary that both will be same, okay. It may be different, okay. It may be different, okay. So then corresponding to dependent observed variables, there is a latent variable called eta 1 and eta 2. So these are symbols like these circles, okay. So now we will connect here, so we will connect like this, okay. We will connect like this, okay. Similarly, we will connect here like this, alright. This is structure of, this is the structure of this is factor model 1, this is factor model 2, okay. So that means this is independent variables, independent latents, dependent variable, dependent latent. So now we have to find out whether there is any path. So let us assume that there is there is a path, okay. This connection will be like this and the connection will be like this, okay. Then the connection will be like this, okay. Then the connection will be like this, okay. The connection will be like this, okay. So this is how. Then obviously there is a relationship, okay, bidirectional, there is a bidirectional. So this is bidirectional, okay, this is bidirectional. Then obviously there is a relationship, okay, there is a relationship, okay. So then we have to know the relationship like this, okay. Similarly we can have also here the relationship like this. Okay, generally it will come like this, it will become like this. Okay, so this is the complete form of this structural equation modeling. This is the complete framework of structural equation modeling. So altogether, so we have 4 different setup. Okay, so first setup is the independent clusters, independent latents, dependent cluster, dependent latent. Then we have to observe this particular structure. So now you have to see here. So this particular setup is called as a path model. This particular setup is called as a path models. Okay, this particular setup is called as a path models. All right, so now so we highlight here, you see here error term will be delta 1, error term will be delta 2, error term will be delta 3, error term will be delta k, then it will be zeta 1, zeta 2, then zeta 3, okay, then zeta k. Okay, similarly there is error term c here. So okay, I in fact these are all regression coefficient, I can cite it here. This one is lambda 1 1, okay, this is lambda 1 2, lambda 1 2, okay, sorry, this is lambda 2 1, this is lambda 3 1, this is epsilon e1, so this will be connected here again. So this is lambda k1. Okay, so this is how the structure is all about. This is lambda k2, okay, this is lambda k3, okay. So this is how these are all regression coefficients. Similarly, this is, you can say, I'll call it, this one is beta 1 1, and then beta 2 1s, then beta 3 1, okay, then this is beta k 1s, okay. Similarly, beta nk, sorry, this is 2k, okay, 2k, this is beta 2 put beta k2. So this is how you have to connect like this one. So then this is, I'll call it gamma 1 1, then this is gamma 1 2, then this is gamma 2 1, okay, gamma 2 3, okay. So then this is theta 2 1, this is theta 2 2, this is theta 2 3, okay, theta 2 3, right, this is theta 2 3, like this. Okay, so this is how, in fact it's a very the model is very complicated. So means ultimately what is our aim is here. So the way we have given the structures, that is how it's called as a structural equation modeling. So here certain things are very much important here. So the structure is itself very important. Then every connection is connected with some weightage, that is we call it the coefficients. So we like to the moment means here the main objective is to find out what are these weightage, all these regression coefficient. The coefficient will highlight what are the variable influence on the latent variable. Similarly, you have to find out the weightage of all these factors here. Then you have to find out the weightage of all these factors here. Then obviously we have to find out the relationship here. So that means we all together. So we have to find out the regression coefficients, and we have to find out the correlation coefficient. For summary, for summarization, so if I summarize this particular you can say model, then obviously there are certain cluster here. So the cluster will be like this way. So one cluster will be x1 up to xk, okay. So this particular cluster is called as a exogenous clusters. It is called as a exogenous cluster, or sometimes it is called as a manifest clusters, okay. So similarly, then y1 y2 up to yk it is called as a endogenous clusters, and again it is called as a endo manifest variables. This is endo manifest and endo manifest variables. This is called as a exo manifest variables. Okay, variable exo manifest variable clusters. Similarly, then epsilon 1, epsilon 2, epsilon 3. Okay, so this particular structure is called as a latent variables. This is called as a latent exogenous variables. Latent exogenous variables. Okay, then another set is eta 1 and eta 2. Eta 1, eta 2. Okay, this is how eta 1, eta 2. This is called as a latent endogenous variable. Okay, or sometimes it is called as a construct endogenous variables. This is also called as a construct exogenous variable. So this is how the full structural equation modeling. So far as a structure is concerned, it's very beautiful. It looks like a very beautiful. The structure identification is very simple, also very beautiful. But the thing is, mathematical derivation or mathematical simplicity is a little bit complex. So it is not so easy mathematically to calculate all these parameters at a time. But so far as the classroom angle is concerned, structural equation modeling to handle in the classroom problem is very difficult. It requires lots of estimation, lots of connections, lots of integration. It's not so easy. So that's why there is a particular softwares. So with the help of softwares, you have to get these results, okay, very easily. So it is sometimes it is very window-based programming. Like there are two beautiful package. You can say that is Amos package and Lizrals. These two packages are very useful for handling structural equation modeling. Okay, so the important thing is that you have to come out with a proper structure. Without having structure, it's very difficult to handle such type of problem, because it's a very interesting problem, very accurate problem so far as a societal problem is concerned or business problem is concerned. Because in a societal problems or business problem, lots of things very integrated, and within that particular setups there may be different structures. So we need to have a close integration with different structure and different integration, so that we can generalize that problems, and that generalized model can be utilized for forecasting and also policy use. Without knowing anything about the proper structure, or you can say proper interdependence relationship, it's very difficult to handle that, which we have highlighted in the case of simultaneous equation modeling. Because if you will apply directly OLS technique to particular equations without having sufficient knowledge on other information about that particular model, then it is very difficult to estimate the parameters. You can do that once, but the estimated parameter will give you biased results, and that model cannot be used for forecasting or policy uses. That's why it's better to find out, either you directly handle the structural equation modeling with the proper structure, with the integration of path model and factor models. So then you will come out with various results of all regression coefficient, correlation coefficient, that is causality and correlations, so that we can generalize in a systematic way. So far as a reporting is concerned, it's very easy to get. The moment you will enter the data, and obviously you can get the results. But the thing is that this interpretation is very interesting here, because so many coefficients are there, so many relationships are there. It's not so easy to interpret it at a time. So it requires lots of intelligence how you to handle such type of problems. This is very complicated problem. The diagram itself is very eye-catching, but so far as a mathematical derivation is concerned, it becomes too difficult to handle manually. So you have to be very careful how you have to handle that particular problem in a software. In fact, the situation is more dangerous when you have series of variables, independent variable, and series of dependent variables, and within that particular series you have a number of latent independent variables and latent dependent variables. Then in that case it is more and more complicated. But the most important thing is that you cannot arbitrarily create so many latent independent variable and so many latent dependent variables. It depends upon your problem formulation, and within the problem formulation how many ways you can prepare the structure, and that structure can be highlighted with the help of the structural equation modeling. So with this, because of lack of time, I have not touched any application part. In fact, briefly I highlighted that issue of education experience and that preparedness, etc. But in a real world, you have to come out with a very proper problem and you have to analyze. So in the meantime, so we have to stop this particular class. Thank you very much. Have a nice day.